Data centers are the backbone of the information age that we live in. The staggering growth of artificial intelligence and machine learning is fundamentally changing how we power data centers. Traditional architectures are reaching their limits, and we're about to experience a major shift. So in our discussion today, we're going to examine how data center power delivery has changed over time, what are the power delivery challenges we face today, and what are the technologies that are being introduced to overcome these challenges. Now let's start by considering what is driving up the power demand in data centers. The compute capabilities of AI and ML processors are increasing exponentially. Now, along with that increase in compute capability comes an increase in power consumption. Now, in the not too distant past, computer processors consumed maybe hundreds of watts. These processors now are consuming kilowatts of power. Add to that the desire to increase the number of processors in an IT rack. This reduces latency in these large AI models and requires an increase in compute density. So the result is that what used to be tens of kilowatts in IT racks are going to quickly move to over 100 kilowatts, and in the not too distant future, over 1 megawatt per rack. Now, when we add this all up at the data center level, the tens of megawatts for a typical data center today quickly becomes hundreds of megawatts and will soon be greater than a gigawatt of power consumed in future AI data centers. This is orders of magnitude increase in power consumption and compute density, and the impact is dramatic. So today, we're going to focus on what goes into data center power delivery. Generally speaking, data centers are powered from the AC grid, and power is converted down to the low voltage DC levels needed to drive the digital logic gates in a processor. So let's walk through this grid to gate power conversion stages and see how the power delivery architectures have evolved over time. Now, for many years, data center power delivery was structured something like this. You'd have a line frequency transformer converting power from the AC grid, which might be taking tens of kilovolts in, and converting that down to some lower voltage level, maybe 480 volts AC, that's distributed within the data center. There might be an interruptible power source at the facility level that provides backup power in the case of grid failure. Next, you'd have some power distribution unit that routes power to each tray in the IT rack. Now, the tray itself would include a power supply unit, or PSU, that typically would have a single-phase AC input, and you might actually have two power supplies used for redundancy. Now, the PSU has two stages. There's a power factor correction stage, followed by an isolated DC-DC stage with typically a 12-volt output. Finally, there's a multi-phase buck voltage regulator and point-of-load buck converters that convert power to the low-voltage supply rails of the processor and other low-voltage loads. Now, this architecture is seen when you have relatively low power loads, maybe processors in hundreds of watts range, and the PSUs probably are rated for maybe a few kilowatts, and the total rack power might be a low tens of kilowatts. And this is what you'd see historically in your generic computing and storage server applications. Now, the next evolution of power delivery introduced a 50-volt bus. This is sometimes called a 48 or 54-volt bus, since the nominal voltage may vary, but the voltage is generally somewhere between 40 and 60 volts. Now, in this architecture, power is converted from AC to approximately 50 volts through the PSUs located on power shelves. Now, the 50-volt bus bar goes down the back of the rack to distribute power to the IT trays. Now, inside the tray is a power distribution board, or PDB, which contains an intermediate bus converter. That IBC converts power from 50 volts down to 12 or 6 volts. Now, this power is delivered to processors through multi-phase VRs. This architecture often includes battery or capacitor backup units in the rack. This architecture is used when processor power is maybe 500 watts to a kilowatt kind of a range, and you may have multiple processors included in each tray. So the PDBs in each tray, they're rated for many kilowatts, perhaps 5 to 10. The PSU shelves are rated for tens of kilowatts, and so when you add that all up, the total rack power might be over 100 kilowatts. But this approach tends to lose steam above around 200 kilowatts. but it's used very commonly in cloud and AI applications deployed today. The question is, when does this architecture break down? Well, it really breaks down when we need more compute density. How are we going to get there? Let's take a look. The first step is to kick out as many of the power conversion components as you can. And the way to do that is to introduce a sidecar rack. The AC to DC PSUs and battery backup units are removed from the IT rack and now placed inside this sidecar. This frees up valuable space in the IT rack to increase the overall compute density. Now, power is distributed from the sidecar to multiple IT racks at some higher DC voltage like 800 volts or plus or minus 400 volts. Now, there may be multiple DC to DC power shelves in the rack that convert from 800 volts down to 50 volts. And like before, there's a 50 volt bus bar transmitting power up and down the rack. Now, the components in the IT tray remain essentially unchanged, as you can see in the diagram. The challenge is that even with liquid cooling applied to this 50 volt bus bar, the rack power will probably be limited to several hundred kilowatts of power. And with the pace of rising compute needs for AI and ML, even this architecture may not be able to cut it. So that leads us to the 800 volt bus rack. In this architecture, we see 800 volts or plus or minus 400 volts DC coming out of the sidecar, and that's being distributed down the back of the IT rack. So this removes the need for any DC-DC power shelves in the IT rack. It does, though, introduce high voltage to the IT trays. This means that the power distribution board, or PDB, will need to be designed with high voltage in mind. The high voltage conversion ratio IBC will convert from 800 volts down to 50 volts or 12 volts, which means that there may be a low voltage IBC converting from 50 volts down to 12 or 6 volts, depending on the architecture. The key advantage of this approach is that it enables very high power delivered to the rack. Over 1 megawatt of power is now possible, and that improves the overall compute density. So now that we understand the high-level architecture, what are the technical challenges to getting to 1 megawatt racks? One of the key challenges is overall grid-to-gate efficiency. Any power that's lost in energy conversion generates heat, and it doesn't go towards the intended compute load. Another key challenge that goes hand in hand with efficiency is power density. Space is limited and power levels are only going up, so this forces the need for increased power density. Performance is also critical. There are large load transients in these systems, and fast response is necessary. With the introduction of 800 volts, appropriate safety measures need to be designed into these systems. Now, last but not least, the power delivery system needs to be reliable and robust. Nobody wants failure of a relatively inexpensive power component to take out a very valuable tray or rack from operation. So next, let's walk through the power delivery system to dive deeper into what changes with the move to 800 volts and what technologies will enable these changes. First, let's look at an example 8 kilowatt PSU that's used today to power 125 kilowatt racks. This has a single phase AC input and a 48 volt DC output, and it shows what a PSU module in a power shelf looks like. Now, this design is uniquely enabled by TI's broad portfolio of analog and embedded products. This design leverages over 15 devices from TI, ranging from gallium nitride power stages and C2000 microcontrollers to digital isolators and high-speed op-amps. The next generation of server PSU designs for AI compute loads looks something like this. Here we have a 30 kilowatt design with a 3-phase AC input and an 800 volt output. This design represents what the AC to DC PSU in a sidecar would look like. Now, to achieve the power density and efficiency targets, this PSU features a 3-level flying capacitor PFC stage and a delta-delta connected 3-phase LLC stage. This design uses over 20 devices from TI, ranging from sensing and control to power switches, bias power, and gate drivers. Next, let's take a look at the battery and capacitor backup units. BBUs primarily support during a loss of power from the grid. CBUs help with load transient support. Think peak shaving or valley filling. Now, for 50 volt systems today, the general structure consists primarily of your energy storage components, your management chips, and some power conversion. Now with the move to 800 volts, the overall structure is roughly the same, but there are some key differences. First of all, there is likely more energy storage needed to support these higher power levels. Also, the control of the DC-DC stage might move from analog to digital since we're moving to higher voltage and higher power designs. Now, isolated DC-DC converter topologies like an LLC might be used in place of non-isolated buck or boost converters. Either way, with these higher voltages and power levels, wide bandgap semiconductors like GaN are of much interest. Now, let's go inside the IT rack and take a look at the power distribution board. Hot swap controllers and eFuses are used to safely control startup and hot swapping. And the latest devices have built-in telemetry, fault protection reporting, and other black box features. Now the IBC may have a regulated or unregulated output of around 12 or 6 volts depending on the architecture. Now these IBC modules typically are rated for around 1 or 2 kilowatts. So what's often done is placing multiple of them in parallel with load current sharing capabilities to increase the overall output power. GaN has been successfully used to achieve high efficiency and power density in these IBCs. Now with the move to 800 volts, we see 800 volts coming directly to the rack. And so the PDB needs to be designed for this high voltage level. You may have hot pluggable inputs that the trays need to be designed for. So they need to ensure that the inrush current is limited and they're smoothly pre-charging the bus capacitance. That's where the hot swap circuit is used to address that challenge and charge those input capacitors of the IBC. Now, the PDB and the IBC, they need to be designed with isolation between the high voltage and low voltage sides. And in the end, what's needed really is a very compact, efficient, and reliable solution because these are located in the IT tray. Here's an example of what the high voltage IBC could look like for an example 800 volt input to 12 volt output scenario. These IBCs are operated essentially as a DC transformer where they have an unregulated output. So for 800 volts in and 12 volts out, it has effectively a 64:1 conversion ratio. Now we can smartly design the converter topology by connecting the two converters with a series input and a parallel output. What that does is it enables us to use 650 volt rated GaN devices in an 800 volt application. Now GaN is a wide bandgap semiconductor that has much improved switching performance and efficiency compared to other switch technologies. But a key part to getting all the valuable benefits of GaN is to actually integrate things like the gate driver, protection, and other sensing capabilities into the device. If you don't do that, you're basically driving a sports car in the slow lane. But by integrating these features, you get the best out of the GaN switch, and you're solving system-level challenges at the same time. Now, let's turn our attention to the final stage in power delivery, which is the multi-phase buck voltage regulator. The key challenges in multi-phase VRs is current density, efficiency, and transient response. Solving these challenges is critical to powering these high current, greater than 1000 amp processor supply rails. So today, in a multi-phase buck voltage regulator, you have a controller that oversees the operation of many parallel phases of power stages and inductors. This controller is very feature-rich, and it has lots of diagnostic and telemetry capabilities. There's typically a large amount of output capacitance that's needed to achieve the power delivery network target impedance. Now, one unique direction that TI has taken is to develop monolithic power stages. These stages integrate the switches, gate drivers, and sensing circuits all in one semiconductor die. Now, in the past, this wasn't feasible, but with the latest semiconductor processes at TI, we have a very compelling solution. Now, add to that the fact that we can integrate the capacitors inside of the package on a lead frame, and we get best-in-class efficiency, the highest power density, and with very good thermal performance, all in an industry standard footprint. Now, one trend that we are seeing in the market is a move from a single-phase power stage to a dual-phase power stage. This helps to pack more current into a smaller space, and that helps to address the current density challenge. Now, TI's dual-phase power stage enables 100 amps per phase peak current, which really helps to address the high peak currents that are seen in these AI processor applications. The next trend that we see is moving from discrete power stages to power modules. A discrete power stage approach, let's say, would have 2 power stages and 2 inductors. And in this example, it's roughly 12 by 19 millimeters and can have roughly 90 amps peak current per phase. We can get that same performance out of a power module that integrates the 2 power stages and 2 inductors into a single component. Now, the dual power stage has a 180 amp peak current capability because you're integrating both of those power stages into the module, but with the overall size being significantly reduced, over 2x improvement in current density, while at the same time reducing the overall height to only 5 millimeters. And this is also in an industry common footprint package. Another trend to address the current density, efficiency, and performance challenges is simply to move the location of the VR. Now, most approaches of today take a lateral power delivery approach, with the VRs on the top or the bottom side of the board. Now, power flows laterally along the layers of the PCB. And because the distance from the VR to the chip can be significant, it leads to a lot of additional power loss and other power delivery network challenges. So a new alternative is to place the VR on the bottom side of the circuit board directly beneath the AI processor chip. Now, this reduces the distance that the high current has to travel, which improves overall efficiency and performance. Now, the vertical power delivery modules may include inductors and capacitors. But the challenge is, how do we make it small enough that it can actually fit on the bottom side of the board? If we're able to achieve that, it frees up valuable space on the top side of the circuit board and overall. As we look to the future, there are several potential future trends in how power is delivered in data centers. One of the key ones being solid-state transformers. A solid-state transformer replaces the big, bulky line frequency transformer with a much smaller, higher frequency transformer that is still efficient. It leverages power electronics to shrink the overall size, and at the same time, it enables higher voltage DC distribution in the data center. This could be at 800 volts, plus or minus 400 volts, or maybe plus or minus 800 volts. Another potential future trend that we see is in the IT tray itself. This approach could be going directly from 800 volts down to 6 volts in a single high voltage, high conversion ratio IBC. Now, the benefit of this is that it enables us to use a lower input voltage to the multi-phase VRs. That in turn enables them to operate at a high frequency, more efficiently, and with higher performance. Lastly, another potential future trend that we see is integrated voltage regulators. What this is actually placing the voltage regulators inside of the AI processor package. How that's going to impact processor power delivery is that you might decide to keep the output voltage of your IBC to maybe 50 volts. And then you'd have a 50 volt down to some low voltage, maybe 1.8 volts. That would be the input to your integrated voltage regulators. This has the benefit of really getting that multi-phase VR as close as possible to the processor, thereby increasing performance. Now, the path forward in data center power delivery is multifaceted. With AI and machine learning demands more and more power, we still need to fit this in a smaller and tighter space. So the entire power delivery architecture, from grid to gate, is being reimagined as a result. This is a pivotal moment for the industry, and we need to rise to the challenge. Innovations in power electronics are needed to unlock the full potential of AI. Thank you.